Hi, this is Gun-Soo Yoon from Pohang University of Science and Technology in Korea. I'll be talking about an exciting new development of RF diagnostics, which can measure the plasma waves locally in tokamaks. Here is outline of my talk. In magnetically confined plasmas, the magnetic energy is often released explosively. In many cases of such events, an MHD eigenmode initially grows like this, which turns into a non-modal perturbation, shown here, and this non-modal perturbation bursts. A good example in tokamaks is the crash of the so-called edge-localized mode. The edge-localized mode occurs in the boundary of high confined mode plasma. The edge-localized mode is like an eigenmode with intermediate toroidal mode number. Our observations using imaging diagnostics on the KSTAR, called ECEI, shows that the Elm eigenmode goes into a transition phase and emerges as a non-modal or non-modal structure with a very low toroidal mode number. And this non-normal perturbation goes into burst. It was well known that the crash of Elm is accompanied by intense non-thermal electron cyclotron emission, or ECE. During our study, we also found that the Elm crash and also evolution are accompanied by intense RF emissions. In the top panel, it shows D alpha emission, which indicates the aftermath of Elm crash. The second panel shows the ECE of spectral component showing the MHD activities, and this very intense emission corresponds to the suprasomal ECE. The bottom panel shows the RF activities measured at 200 MHz and 400 MHz. And as you see here, the RF emissions modulate in correlation with the MHD activities. And the RF emission peaks at the time of the Elm crash. While we want to study more closely the RF phenomena at the time of the Elm crash, there was clear limitation in the way we measure the RF emissions, namely the measurement using the external dipole type antenna. We are not able to locate the exact position of the radiation source. In addition to that, the bandwidth of the antenna is limited. Furthermore, we cannot measure electrostatic waves because electrostatic waves doesn't come out of the tokamak, nor the waves that are absorbed by the plasma along the way to the antenna. In order to overcome such limitations, we considered whether we can measure RF waves embedded in the form of modulation of ECE. If that's possible, then we'll be able to measure the plasma waves locally and with extended frequency range. So we have built an RF diagnostics utilizing the ECE imaging system and a very high-speed digitizer. Inside the ECEI, there is an array of millimeter wave mixers, and the IF signal is directly digitized by this high-speed digitizer. It has up to 40 gigasamples per second sampling rate with 10 gigahertz analog bandwidth. And the typical acquisition time is about 100 milliseconds, which gives better than 1 megahertz resolution. Using this RF detection system, we were able to measure waves embedded in the non-thermal ECE during the Elm crash. Here is a typical example showing very broadband intense emission during the crash. Moving into the details, the emission contains both very broadband and very intense narrowband emissions. And the narrowband emission shows repeated rising and falling patterns and eventually disappears. We also found that there is high coherence at the frequency of the narrowband waves, indicating that the broadband waves are swayed by the narrowband waves. We also measured the poloidal wave number of the emissions using the two vertically adjacent channels. And we found that the poloidal wave number is compatible to the Whistler wave number, assuming the cold plasma condition and nearly parallel propagation. But the question remains about what we are actually measuring. First, remember that the signals we are acquiring is the intermediate frequency signal from heterodyne mixing. The IF signals can contain both frequency and amplitude modulations. So the question is whether it is possible to distinguish the two different kinds of modulations. The amplitude modulation is relatively easy to understand. The omega 1 is the carrier frequency, that is the intermediate frequency, and let's call omega 2 the frequency of the amplitude modulation. Then we can easily see that the modulated signal contains three components: the original carrier frequency and the sum and difference between the carrier and the modulation frequency. The frequency modulation case is a little bit harder but can be understood analytically. The frequency modulation can be represented similarly, but note that this is not the amplitude modulation but the frequency modulation. So we have to integrate the phase of the modulated signal like this, and going through some trigonometric algebra and using Jacobi-Angher identity, we can find that the ultimate modulated signal contains the harmonics of the modulation frequency. So here omega 1 plus the integer times omega 2, and another term containing omega 1 minus the integer multiple of omega 2. If the ECE signal is frequency modulated, it will appear as harmonic lines of the modulation frequency in the spectrogram, as mentioned. In the case of Elm crash, we don't see harmonic structures in the spectrogram. So we can say that what we are observing is the amplitude modulation of ECE. But in some cases, like runaway condition, we do see harmonic lines, which implies the frequency modulated ECE. Here is an example showing very regular harmonic lines in a runaway condition in ohmic discharge. There is highly regular harmonic feature. The spacing between the harmonic lines is about 15 megahertz. There could be multiple interpretations, but one possible interpretation is superthermal population of electrons circling around the torus. In such condition, the electron cyclotron emission can be relativistically modulated, and for such condition, we can estimate the 15 megahertz spacing corresponds to the electron beam energy around 100 kilo eV. Here is my summary. We demonstrated the local measurement of high frequency waves utilizing millimeter wave mixers. Plasma waves can modulate ECE intensities, which can be detected by millimeter wave superheterodyne mixing and modern high-speed digitization technology. We expect the combination of existing ECE imaging and this new RF diagnostic schemes can provide comprehensive data for the fast relaxation process of imaged modes with unprecedented detail. We also expect the same scheme can be used to detect phenomena that can cause frequency modulation of ECE, such as suprasummal electrons in runaway conditions. Thank you very much for your interest.